I think we've started a new screen recording. Looks like we've got it going. And I'm sorry that this has been so long in the coming. I've been extremely ill for the past few days. It's been a rather unpleasant experience. But this will be our last chapter, chapter 17, Physics of Hearing. And great picture here to illustrate this chapter. If a tree falls in the forest and no one's around to hear it, will it make a sound? Of course it makes a sound. By the definition of sound, sound is a propagating pressure wave in a material, and most of the sounds that we hear are propagating pressure waves in air, which is the material. But sound also travels through liquids and solids, in many cases much better than it travels through air. So we're going to be learning about sound in this chapter. We've got 7 sections, I think. Hold on a second, loud truck. I'm making this video outside because it's nice and cool on the front porch. But that means that we have to deal with the sounds around us here, and sounds like a not so well running diesel truck driving by. But anyway, let's take a look here what we've got. We've got the famous breaking the glass experiment by sound resonance, which we saw in the last chapter. And why does it happen? Well, because of this building compression wave within the material that builds on itself as it bounces back and forth, which we call resonance. And of course, we saw that on a string. But here we can see a little illustration of how a string creates a compression wave in air. The string is the black line in the middle, held in place by these 2 little brown pieces on each side. And as it vibrates back and forth in this, notice that it's in its first fundamental mode, where it's just one big antinode waving back and forth between the 2 nodes here at the end. As the string moves back and forth, it does compress the air in the direction that it's moving, so on the right-hand side in this case. And on the left-hand side, the vacuum that it leaves behind is what we call rarefaction, or kind of a lack of compression, a lack of compressed or decompressed air. And so you have a wave where you have compressed, decompressed. And then, as the string goes the other way, it compresses the other side. And so that rarefied air that was made previously is now moving forward, but the string is making compressed air in its wake, and so you get rarefied compressed, and on the other side you get compressed rarefied. And so and then the string just keeps going back, oscillating back and forth and back and forth and back and forth, creating compressed, then rarefied, then compressed, then rarefied, compressed, rarefied. And these things move outward because the string has pushed the air outward, and you get a traveling wave of compressed and decompressed air. Here you can see that a little bit more here. And then we use an actual transverse wave to demonstrate this, where the y-axis is the compression of the wave, and the x-axis is the position of that compressed air. And so it looks like a sine curve again, instead of just compressions and decompressions. So high is compression, low is decompression, high is compression, low is decompression, and so on and so forth. The way that we hear this is that these compressions and decompressions, compressions being the solid lines, decompressions being the dotted lines, they enter our ear canal, and as they go through our ear canal, they press against the eardrum, and the eardrum is essentially a flexible membrane that is stretched across our ear canal, and that feels a force from the compressed air inward, and it feels a force from the fluid on the inside of our ear outward. When it feels the compressed air is generally stronger than it generally exerts a force stronger on our eardrum than the fluid inside of our ear exerts, and so it presses the eardrum inward. And as it presses it inward, there is a bone inside of there that is connected to a nerve. And let's see if they have a nice picture of that. They don't have that, but we'll probably see that later. I think that there's a picture later on. But anyway, right up in here inside the ear canal, there is a series of bones. It's not just one bone, but there are these tiny little, very delicate bones that are connected to the eardrum, and they're called hammer and anvil, and maybe one of, I can't remember what. Well, anyway, they're actually their real names are much more complex than that. But anyway, these bones move, and they actually kind of tap the aural nerve, or the hearing nerve inside of your ear, as your eardrum moves back and forth in this compressed and rarefied air. As the compressed air comes into your ear, of course, the fluid on the inside of your ear pushes outward, and it has the opposite effect than the other one. And it happens very quickly at high frequency, so that you can hear different tones of sound and so on. So how do we deal with the speed of sound, the frequency of sound, the wavelength of sound? Well, really, same way we deal with the speed of any wave, the frequency of any wave, the wavelength of any wave. All the relationships are the same. Velocity of the wave is still frequency times the wavelength. Frequency of the sound wave, of course, depends on what is the tone of the wave, and there can be pure tones of wave, pure frequency waves, sound waves, or there can be mixtures, and most sounds that we hear are mixtures of frequencies. But a tuning fork is one way that you can get a pretty clear single frequency of wave. It's not perfect single frequency, but it is mostly a single frequency. And so if you've ever used a tuning fork, you know what I'm talking about. It's a very clear and very simple tone. Most digital music that you hear from old video games and so on and so forth, the beeps and the boops and all that stuff from the old video games, those are single frequency tones, and that kind of gives them their characteristic computeristic sound. That characteristic computer sound is that single frequency tone. Most musical instruments are very multispectral. In other words, they have a lot of frequencies mixed together, and that's what gives them their characteristic sounds. Each instrument has a different mixture of frequencies. What is the speed of sound? Well, it depends on what it's traveling through. As it travels through air and other gases, you can see that it has different velocities. Through air, oxygen, carbon dioxide, it's all 250 to 350 meters per second. Helium, it starts to travel a lot faster. Hydrogen, faster still. Liquids has a tendency to travel fairly fast. 1160, 1450, 1480, 1540, 1540. Right? And solids fairly quickly as well. Although vulcanized rubber, it travels very slow. Most other things, it travels fairly quickly. Steel, it travels 5960 meters per second. So very quickly through steel. But every material has its different properties for sound, the speed of sound. At the bottom of this here, they talk about earthquakes, and because earthquakes are essentially sound waves traveling through the earth, and they have two different kinds of waves that travel through. One is called a P wave, one's called an S wave, and they talk about that just really quickly here. I can't remember how much we talked about that in the last chapter, but they are a type of compression wave or a sound wave. Very low frequency generally. Sound wave, but they are a type of a compression sound wave. But another thing that they talk about is the temperature of a material affecting the speed of the wave, and that is definitely the case with sound. Sound is affected by temperature because the speed of the molecules in the material are affected by temperature, and then carried by the movement of the molecules. So if they're moving fairly quickly, it's going to increase the speed of the sound. So here they give us an equation for calculating the speed of sound in air at different temperatures, where T is the temperature, 331 meters per second is, and that temperature is in Kelvin, by the way. 331 meters per second is the speed of sound in air at 0 degrees Celsius, which is 273 Kelvin. So you can see here, if your temperature is 273, you'll get 273 over 273 squared root of 1 is 1. You'll just get the normal speed of sound. This is the VW is velocity of the wave, so it's the wave speed. And here they give us an equation for the average speed of sound in a gas related to the average speed of particles in the gas. And so they have 3 times K, which is Boltzmann constant, times T, temperature in Kelvin, divided by the mass of the particle. Let's see, is it the total mass of the gas, or the mass of the particles? Does it say? Yeah, masses of each identical particle, so the mass of just one particle in the gas. And so that's a useful equation too, to give you the average speed of sound in a gas, any gas. Here they show an image of how a bat uses sound to its advantage to find things. It always is sending out this high frequency sound wave, compression wave. That's the blue wave that it sends out. And these waves bounce off of other creatures and bounce back to him, where he can detect it with his big old ears. Now the way that he determines where it is by his ears, because he has stereo ears, 2 ears. His brain can triangulate and figure out where the bug is, and that is something that we can do as well. We can tell where sounds are coming from because we have a stereo hearing. So that's not something that should be hard for us to figure out. But the thing that it can do is the thing that a bat can do is also figure out which direction the bug is moving, and also how fast it is moving. And that comes from something that we cannot do, and that is they use the Doppler effect to their advantage, which we'll learn about later. So here we have a speaker that is sending out 2 different frequencies. One frequency from its large cone and one from its small cone, and we're going to superimpose these frequencies, have them just playing right on top of each other. And just like with the other waves that we made in strings or in water or whatever else, you can do that, and the frequencies can be superimposed on top of each other, and then they can run right through each other, and they'll be completely unaffected by it. It doesn't bother them at all. They can be mixed and unmixed and everything else. And so, not a big deal. Let's go through an example of calculating wavelengths. This is nothing more than we've done in the other chapter that we did on waves, except that we're going to use this particular equation for waves in air. We have we want to calculate the wavelengths of sounds at 20 hertz and at 20,000 hertz, which are the extremes that we can hear at 30 degrees Celsius air. Well, we're going to calculate the velocity of these waves in 30 degrees Celsius air by using the equation that determines velocity at temperature. So it's going to be 303 Kelvin instead of 273 Kelvin for 30 degrees Celsius. And then once we got that velocity, we plug into the equation for frequency, velocity, and wavelength, solving for the wavelength. And then we plug those in for the 20 hertz and the 20 kilohertz, 20 hertz and 20,000 hertz. 17 meters and 1.7 meters for those 2 wavelengths. So So low notes that we can hear, the very lowest notes are really quite long. 17 meters long is nearly, I mean, we're getting up into the 40-foot long range, almost 50-foot long range waves. And that doesn't surprise us then that, pipe organs, for example, and tubas and very low instruments have very, very long tubes that the sound is made in for the sound to resonate in. A tuba is something like 20 some odd feet long, and an organ pipe can be something like 30 and 40 feet long. They have to be that long to create a wave that long. So now how are we going to measure the level of sound, intensity, loudness, so on and so forth? Intensity we've already defined in previous chapters as the power per area, where power is the amount of energy per time. And sound is a form of energy, and so we should be able to calculate how much energy per time is going on, and that would be our power. And the area would be essentially the area across which we are detecting the sound, or releasing the sound, or absorbing the sound, or channeling the sound. Whatever we're doing with the sound, we're going to be doing it in some area, and that would be our area in the equation. Excuse me. They go through some mathematics that involves some calculus, and give us another definition which involves pressure, change in pressure and density and volume. Sorry, not volume, velocity. And they give us this equation here. Intensity is delta pressure squared over 2 times density, or the density is the density of the material the sound is traveling through. And the v is the velocity of the sound wave there. And here they have a little demonstration of intensity, where you have a bird making a little tiny little twitter, and you have this small little wave here, and another one making a really loud one. It's the same frequency. In other words, the wave waves back and forth the same number of times in this short distance, but the amplitude is way bigger, is much, much bigger. And that amplitude is directly related to power and intensity and other things like this, and loudness, really. But it's not the only part of the story. Because intensity is power per area, and power is watts, then power per area is going to be watts per meter squared. But watts per meter squared gives us an extremely huge spectrum for sound intensity. And what I mean by spectrum is I mean this right here. At the smallest sounds that we can hear have an intensity level of about 1 times 10 to the minus 12 watts per meter squared. It's a very small number, 0.0000000000001. It's a very, very tiny little number, watts per meter squared. But, and that's the smallest sound that human ears can usually hear. And the loudest thing we can hear is 1 times 10 to the 4th, which is 10,000. And that's where our eardrums literally rip and break. So you have this extremely very small number at one end, and this fairly big number at the other end. And we don't want to use that huge range of numbers to describe sound. We'd much have, especially since sound is so normal, everyday kind of stuff. Everybody, deals with sound all the time. So instead of dealing with this huge range of numbers, we're actually just going to deal with the numbers that are in the exponent. And so we could start with negative 12 and go to 4, and have a scale that goes from negative 12 to 4. But instead of doing that, we call negative 12 0, and we just go by tens all the way up to the highest, which is 16 later. So it takes us to 16. So there's essentially 17 levels, including the 0 level, and that's how we go. But notice that we're not jumping by normal kind of amounts. Every time we jump from 0 to 10, for example, we go from 1 times 10 to the minus 12 to 1 times 10 to the minus 11. So 10 is 10 times bigger than the 0 level. And 20 is 10 times bigger than the 10 level, not twice as big as the 10 level. And 30 is 10 times bigger than the 20 level, because what do we have on the left side is what we call a logarithmic scale. And so we use this scale a lot in hearing, and we call it the decibel scale. And it actually has a mathematical definition. Decibels on the left-hand side of this equation here, which we use the symbol beta for decibels, is equal to 10 times the log base 10 of the intensity of the sound I over I0, which is our base intensity, which is 1 times 10 to the minus 12. So if you plug in whatever intensity you have in watts per meter squared along these numbers here, divide it by 1 times 10 to the minus 12, take the log base 10 of it, multiply it by 10, then you will get this number over here, which would tell you the sound level intensity. And you might not get exactly 10, you might get 11 decibels or 23 decibels, something in between the 10s, but that's how the decibel system works. And it's a little bit confusing to people at first, and people are sometimes perplexed. Why would we use the scale? Why would we use a scale where 10 decibels is twice as intense as 0, 20 decibels is twice as intense as 10, 30 decibels is twice as intense as 20? Well, because to our ears it doesn't necessarily sound that way. Something that is 10 decibels and something that is 20 decibels do not sound, I mean, the 20 decibel thing does not sound 10 times louder to our ears and to our brain. It's actually more kind of like double. And it's not, there's not really a way to quantify it, but our ears and our mind adjust for sounds as they get louder and louder. As sounds get louder and louder, our brains and our ears literally kind of combat it. They work against that to prevent damage to our eardrums. So if you're spending a lot of time in a loud arena at a concert or something, your ears will actually fill with fluid to back pressure your eardrums to prevent your eardrums from breaking. So it's much easier to break your eardrums from a sudden loud sound while you've been listening to not much, pretty quiet, having a quiet life, than to be at a rock concert all day and then hear a loud sound, because your ears have been prepared and your ears have been constantly filling with fluids to prevent damage to your eardrums. And so it's kind of interesting. Our ears work in a very interesting way. They work in a more logarithmic way, so this system actually does make a lot of sense for the way we work physiologically and also mentally. So let's take a look at a couple of things. First of all, this little chart here is kind of important, because if you double the intensity of something, it doesn't change. It doesn't change from 10 to 20 or from 20 to 40 on the decibel scales. If you double the intensity of a sound, it actually changes it by 3 decibels. So if you're at 17 decibels and you double the sound, it goes up to 20 decibels. If you're at 23 decibels and you double the sound, it goes up to 26. And so these intensities are important to remember, this little table. If you increase by 5, by a factor of 5 times as intense the sound, then it increases by 7 decibels, and of course 10 times as much as 10 decibels change. So let's calculate some sound intensity levels in this example here, and get used to using this equation that's related to the decibel scale and also these ratios. Oh man, I can never stop yawning. So they want us to calculate the sound intensity level in decibels for a sound wave traveling in air at 0 degrees Celsius. And they tell us the pressure amplitude is 0.656 Pascal. The pressure amplitude is our delta P, our change in pressure. So intensity, of course, is going to equal delta P squared over 2 times, they have a P here, but it's supposed to be rho for pressure, for density. So 2 times rho times velocity of the wave in air. So we know that the speed of sound is in 0 degree air is 331 meters per second. We also know that the air has a density of 1.29 kilogram per meter cubed at atmospheric pressure and 0 degrees. So we can plug in all those numbers into our equation and get the intensity of the wave at 5.04 times 10 to the minus 4 watts per meter squared. Now, that's the intensity. We want the sound level. And so we use this intensity in the equation for sound level, whereas the beta, or the decibels, is equal to 10 times log base 10 of our intensity I divided by intensity naught, which is 1 times 10 to the minus 12. Once you plug those numbers in, you will get 87 decibels. Right? Because it's 87, it has that 7 extra decibels above 80. 87 decibels is 5 times greater the sound level than 80 decibels, because 7 decibels is equal to a 5 times ratio difference. Here's another example. We're going to change the intensity levels of a sound and what happens to the decibels as we change the intensity levels. We have a sound is twice as intense as another, and we want to show that it's 3 decibels higher. So we have intensity 2 over intensity 1 is going to equal 2, and we want to show that that makes a difference in the betas, or the decibels, of 3 decibels. So we take the log base 10 of B minus the log base 10 of A, and if you remember your logarithmic identities or logarithmic tricks, the bag of tricks, that is equal to log base 10 of B over A. And so that would be the log base 10 of I2 over I1, and I2 over I1 is of course equal to 2. Log base 10 of 2 times 10 is always going to equal 3, because the log base 10 of 2 is 0.301 times 10 is 3.01, and there we have it. It's not exact, but it is, it's good enough, right? Okay, so now the Doppler effect. The Doppler effect is something that all human beings have experienced, for a very long time. As long as things have moved quickly that had sound associated with them, we've experienced this effect, but not maybe understood why it happens. Here they have a picture of a car passing by 2 people who are standing on the side of the road. And the sound is coming away from the car in these waves, where these lines represent the peaks of pressure intensity. And they will eventually reach both of these people as the sound moves sideways and the car moves into or out of the page, depending on how you want to think about it. However, if the 2 people were standing in front of and behind the car, it would be a different picture entirely. Because as the car is moving forward, the sound is also moving forward, but the sound is moving forward at 331 meters per second squared if it's 0 degrees outside and it's air. But the car is also moving forward, and it might be moving forward at 30 meters per second. So it's like catching up to those waves, or it's kind of, it's not quite catching up, I guess, too, but it's moving behind it. And so in other words, what really happens is that the waves get kind of squished together. They get closer together in front of the car. And behind the car, they get further apart, because the waves are moving away from the car in the other direction. And so the further the wave is from the car, the further the waves are apart. And it creates an interesting effect, because this spreading out of the waves actually changes the frequency of the sound. Because the waves are further apart, they're not going to have as high a frequency. So it's going to change the tone of the sound if it changes the frequency of the sound. And the same would happen if the people were running towards the sound. If the girl here is running towards the sound, she's going to encounter each wave peak more often, and so the frequency of the sound will be higher and the tone of the sound will be higher. If this man over here is running away from the sound, then he's going to encounter the waves less regularly, and he is going to experience a sound that is lower in frequency. And this is called the Doppler effect, this changing of frequency as objects move relative to each other that are emitting sound waves or pressure waves. And it's actually a relativistic effect that is not that hard to figure out. It's relative speeds of objects moving, and it's very, very similar to throwing the baseball off of the train, the moving train, for example. It's pretty much the same thing, actually. You're just throwing sound off of moving objects and catching sound with moving objects. In the end, you also get a very similar equation, except we're not going to try to solve these equations for speed. We're going to solve them for frequency, because this frequency is what we're really interested in when it comes to waves. And so here we have an equation for the frequency of a source of sound that is moving and a stationary observer. So the frequency that the observer hears is frequency observed here, observed, FOBS. And the F sub s is the frequency of the source, where the source is actually moving. And here we have the velocity W, velocity of the wave, that's the velocity of sound, and then the velocity of the source, Vs. Now, if the source is sitting still and the observer is moving, the equation is different. The observed frequency, or the frequency that is measured, is going to equal F sub s, and this ratio in here changes, you can see. It flips over and some things change about it. So two different equations, one for moving source, one for moving observer. And there's actually an equation that is for moving source and moving observer. I don't know if they show us that one. But here we do an example. So we have a train that has 150 hertz horn. It's moving at 35 meters per second in still air on a day when the speed of sound is 340 meters per second. Turns out that all these equations do assume that the air is not moving. There's no wind, because wind does change things. And in part A, they want us to know what frequencies are observed by a stationary person at the side of the tracks as the train approaches and after the train passes. And B, what is the frequency observed by the train's engineer traveling on the train? So two things here. So in part A, we have a stationary observer moving train, but the moving train is moving towards him or away from him different times, right? So that different things. And that matters because the sign of the velocity is going to change things. The velocity is the source. And actually in these equations, I didn't mention this, but it's obvious, there are pluses and minuses here. Pluses and minuses. And the pluses and minuses are actually for motion toward and motion away from the observer. So the minus sign in the first one, the minus sign is used for motion toward the observer, and the plus sign for motion away from the observer in this first one. In the second one, the plus sign is for motion toward the source, and the minus sign is for motion away from the source. And so you have to read the fine print to figure out which equation to use. So as the train is moving toward the person, we're going to use the minus sign to start, and that's what they do right here. And we plug in our numbers, and we get a frequency of 167 hertz, which is a higher frequency than we started. We started at 150 hertz. And that's to be expected, because as something comes towards you, the frequency is higher. Think of as a motorcycle comes towards you, for example, you hear this mee, and then as it goes past you, it goes meow. It goes down in frequency. And so it starts high and then it goes low. And so this is what we would expect. Same thing happens for an ambulance or a fire truck. You hear the high rotating siren first. It goes wee 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 wee, and then as it goes past, it goes wee 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 as it passes you. And that goes from high to low. So in part B, we are going to use the same equation but with a plus sign, and we find that gives us 136 hertz, which is a lower frequency, lower tone, and so that's what we would expect. So, what is a sonic boom? Well, They usually have a demonstration of this using a motorboat, a ski boat first, and I like that better. Let's see if I can't really find one here. Oops, I dropped the broom. Sorry. Anyway, everybody who has ever been on a boat knows that a boat leaves a wake behind it. And the reason the boat leaves a wake is because the oscillating propeller puts waves into the water, and the waves travel outward behind the boat. But the boat moves much further forward than the waves move outward from the propeller. And so it leaves the waves leave this kind of triangular shape in the water as they move outward, but the boat is moving much faster forward. The same thing happens with very fast planes, very fast airplanes and their sound. So if you have a very fast airplane moving forward through air, its engine is making these sound waves that are traveling outward, but they're just getting left behind. And let's find a good sonic boom applet here. Maybe we can find one online that will work for us. There's some pretty good ones out here, so hopefully we can find one. Let's see if this one works. This one looks like it's working for us, so that's great. Okay, so we're going to start by showing the Doppler effect. And what I've got here is I've got this red dot, which is kind of like our boat on the water, or our jet plane in the sky. Let's talk about a boat first. And so this is a boat traveling very slowly. And this is how they always ask you to travel when you're close to shore, close to swimming areas and things like this, close to places where boats are mooring, close to all of the docks and everything. They want you to leave no wake, right? And so what you do is you try to travel slower than the waves from your propeller do, so that the waves from your propeller are traveling outward in all directions, and they're traveling faster than the boat is traveling. And what happens when you do that is that you get these little ripples that travel outward from your boat in all directions, but you don't get these big ripples behind you. You don't get big waves behind you. And down here we can control different things. We can control these. I guess we can control the position of our. Here it looks like we can control. I'm not sure what we can control here. Maybe we can't control anything. Let's see, where can I download this puppy? Here, let's see if we can open this up in the proper way here. Sure is taking its time opening up. All right. Well, it's not going to let me open it, I guess. Not sure why. Well, I guess I'm not going to get lucky finding an applet that works. We'll try one more and see if we can force it to work for us. I guess we're just not going to be able to. It kind of drives me crazy. Oh well. At some point, people are going to have to update these and make them work because they're great. Maybe I'll have to learn to program in Java and do it myself. I have not done so. I have not learned Java. Maybe this will work. Doesn't look like it. Well, it's okay. Let's use this one because it kind of illustrates it anyway. So here we have our jet plane moving along. Its sound is emanating, and as it moves forward, the sound waves get closer in front and further apart and back. And this would be like traveling in the zone where you're not allowed to make a wake, so that your sound waves are traveling faster away from you than you are moving forward. But as you get going faster and faster and faster, you start kind of compacting these sound waves into this huge barrier in front of you. And keep in mind that each one of these lines represents a high pressure zone, so there's a lot of pressure in front of you. And that happens with a boat. You get to a point where you're moving almost fast enough that you're ready to start making a wake, but you kind of have to jump over this big wave that you're pushing in front of you, and so you can start hydroplaning essentially. Then you get to this point where the pressure waves are stacked up as big as they can in front of you, and you can start to see that there is this stack of pressure wave here and here. And that is where you start to really jump. You're starting to jump over this pressure wave, and you're going to stop. You're going to leave the region where you're traveling slower than the sound you make or the pressure waves that you're making in the water if you're a boat. So this is essentially the sound barrier. The jet and the sound are moving at the same speed, so the jet is catching up to the sound right here all the time. Once the jet breaks through that pressure wave, or what we call the sound barrier, it's moving faster than the sound, and so every little sound that it makes gets left behind. And so each one of these circles represents a sound wave that is moving outward from a point that the jet used to be at. And now you get pressure waves that build up along these lines here. See all these blue lines that stack up on each other, and that is the wake of the boat or the sonic boom of the jet, because this line of sound here is really strong. It's a lot of pressure waves stacked together. There is actually more right before you break, and so right before you break the speed of sound, or right as you break the speed of sound, there is a great big pressure wave that goes boom through the air, and that's the sonic boom. And then there's another one that keeps going. It's not quite as loud, but it still is loud along this edge. As this edge reaches the ground, as it goes further and further down and reaches the ground, it does create a sound that is quite loud if the jet is moving at the speed of sound. This is one of the reasons that jets that are traveling the speed of sound have to be very high up, so that that sound has time to dissipate before it hits the ground, so that it doesn't hit the ground with a big, big, loud bang. And this is what they call the bow wake of a boat, or the sonic boom of a jet. And it is a result of the Doppler effect, the result of the object that makes the sound catching up with the sound that it's making, and then even passing it. And so here they show that as well. Here they show it again. You have one that happens from the tip of the plane, one that happens from the back of the plane. In the back of the plane, one is generally louder because that's where most of the sound comes out. Now, this sonic boom is more than just a loud sound. It is a big pressure wave, so it can actually cause damage. It can break windows. It can actually it can cause a lot of distress with people. In fact, the military uses this all the time to intimidate people that are trying to flex their muscles. They'll send a bunch of jets, a bunch of big bombers usually, that at supersonic speeds, and they'll fly them very low over a boat or a ship, and it'll knock things down, it'll break, delicate equipment, and it'll scare a lot of people because it's kind of like a little earthquake. It's a pretty big deal. Okay, so now we're going to talk about how sound resonates in air columns, and this is essentially kind of musical instrument science here. And it's very similar to vibrating waves on strings, except we're going to have waves that are going to bounce back and forth inside of tubes, essentially. So here we have a tube. It's a hollow tube, and we have a tuning fork, and we're going to strike the tuning fork next to the tube. And the tube is going to be closed at one end and open at the other. So it's open at the end that the tuning fork is at, and this end right here is capped off. As the tuning fork vibrates and makes a sound wave, it creates this sound wave that we're going to represent in kind of these cones, where the small part of the cone is going to be a small amount of air movement, or in other words, well, let's say that the small area is small pressure and the big area is big pressure. That's what we'll call it. And so we have low pressure here and big pressure here, and it goes down here to the end of the tube, and then it bounces back so that you end up with big pressure down here and small pressure down here. And there you have it. Now, if the wave, which is represented kind of by the curvature of this cone, is about the right size to fit into this cone, so that you get at one end you get a minimum and the other end a maximum for an open-end tube. Then you can get what we've been calling resonance. In other words, the wave fits just perfectly so that as it bounces back and forth, it builds on itself, and the wave amplitude gets bigger. In other words, the sound gets louder. And for an open-end tube, for a closed-end tube, one that's closed at one end and open at the other end, it turns out that this type of wave that goes from this minimum to this maximum amount is essentially the fundamental wave, or the largest wave, the longest wave you can fit in that tube. And why is that? Well, because at the closed end you can't really move the air around, and so there's going to be a minimum amount of movement, and that's what is represented by this node, is a minimum amount of air movement, because it's closed. You can't, once you get to that end, you can't do anything at the end. However, at the opened end, you can get a maximum amount of air movement. Air can go out, air can come in to the tube there. And so this represents actually only a quarter of the total sound wave. And that's very interesting, because if the wavelength is, let's say, 1 meter long, you can resonate a 1 meter long wavelength in a 1/4 meter long tube. which is really kind of phenomenal. We've already said that, sound waves can be 17 meters long in normal conditions. Well, to resonate a 17-meter long wave, you only need a 4 or 5 meter long tube. You only need 1/4 of that distance as long as that tube is closed at one end. And so that's what they do with very long instruments. They close it at one end and they make it 1/4 as long as the wave. And it turns out that it actually creates a different sound than if you open the tube at both ends, which doesn't allow as long a wave in the tube. But so you have different things going on. But it's still very interesting. So one way to do this is actually to just open a little hole here at this end where the sound can come in, and then resonate it in the tube where this end is open and this end is closed, and a quarter wavelength fits in, and so whatever 4 times the length of this tube is the resonant wavelength of the fundamental for that tube. Now, of course, tubes are going to be just like anything else with waves. In other words, you're going to be able to fit different size waves in them as well because of nodes and antinodes. So, for example, the only condition that really has to be met is that at the closed end we have no movement, and at the open end we have lots of movement. And so you could fit a wave like this, where 3/4 of the wave fits in the tube. And this would be the next one. This one has one node, whereas the previous wave had 0 nodes. Well, this one could be one node, and this one could be 2 nodes. 2 nodes and 2 antinodes, and this is 1 node and 1 antinode. Here you have a quarter of a wave fitting in the tube, and the wavelength, the fundamental wavelength of the tube, is 4 times the length of the tube. And this one is the first harmonic of an open-end tube, and then 3/4 of the wave fits in. And the second one, you put in 3 nodes and 3 antinodes, and this one you have 1 1/4 wavelengths fits into the tube, so more than a single wave. In this one you can fit in 7/4 of a wavelength, so almost 2 full wavelengths in the tube, and so on and so forth. And so for a closed-end tube of length L, the fundamental wavelength is equal to 4 times the length of the tube. The first harmonic, or the first what we call overtone in music, is 4/3 the length of the tube. The second overtone is 4/5 the length of the tube. The third overtone ends up being 4/7 the length of the tube, and you can keep going with that. And it actually has a formula that looks like this. Maybe you've already noticed the pattern, but the formula looks like this. The resonant frequencies in a tube that is closed at one end, F sub n, where n is the number of the harmonic, the first harmonic being the fundamental, second harmonic being the first overtone, and so on and so forth, is n times the velocity of the wave, so that's the speed of sound, divided by 4 times the length of the closed tube, where n is equal to 1, 3, 5, 7, 9, and so forth. So that's your very first introduction to musical instruments. And what kind of things include closed tubes? Well, the voice is a closed tube. The inside of your body is, of course, the end of the tube, the inside of your trachea, and it essentially ends at your vocal cord, larynx area. And your mouth is the open end of the tube, and it has different overtones that resonate with that. Pause. You have a question? I'll come in. Okay, I'm back. Sorry for that, but I had to go answer a couple questions. Um, so anyway, so in this example, they want us to find the length of a tube with this 128 hertz fundamental. Well, they tell us the fundamental frequency. We plug that in for n equals 1 into the equation, and we get a length of the tube, solve for the length of the tube, and L will end up being, in this particular case, plugging in all those numbers, 0.672 meters, so a little more than a half a meter. And to find the the fourth overtone, you take the fourth number in the fifth number in the series, 1 being the first one, then 3, then 5, then 7, then 9. So 9 is the fourth overtone. So F sub 9, plug in the numbers, you get 1.15 kilohertz. Now for an open tube it is different. Notice that for an open tube you can fit in, on both ends, you're going to have a maximum amount of movement of the air, because if both ends are open, both ends of the tube are open, then both can vibrate. And so your first fundamental ends up actually being not a quarter of a wavelength, but a half of a wavelength. And so your frequencies and overtones, your fundamental and overtones, start to look different, and the equation looks different as well. And the equation for this is n times VW over 2 times L instead of the 4 times L. And then n equals 1, 2, 3, 4, 5. It doesn't skip numbers, and it's not all odds. And so you have a different kind of deal. And not only do you have a different deal, but because you have different types of overtones, you have a different sound. So, for example, your pipe organs will have a set of pipes that are all closed pipes, because that gives you a different sound than open pipes. And then they'll have another set of pipes that are all open pipes. And then they also use different shapes of pipes, which make different effects, do different things with the overtones as well. Open pipes, closed pipes, different deals, and different instruments use different things for those. For example, here you can see that you have the bars on this instrument create the vibration, but these funny shaped tubes, which are actually gourds, are going to create the resonance. So these are closed-end tubes, but they're a funny shape, so they're going to have a very different sound than tubes that have be straight with a closed end, and would be a different sound than tubes that are straight with an open end. They have different resonant qualities. So in 17.6 we're talking about hearing, and here we're going to talk less and less about, we're going to have less and less calculation, more and more just how this works. And here they're using the decibels again, so that's nothing we've not done before, just a review essentially. Although the decibels of hearing, what they're talking about here is actually using these charts, because the sound level that you hear depends on the frequency. So you have a chart of frequency versus sound level. So our ears hear certain frequencies very easily. In other words, they sound very loud to us, whereas other frequencies do not sound so loud to us. And that essentially is kind of a mental perception. It's a brain thing. So anyway, you got to look at those charts to figure those things out. It's not that challenging, I would think. Doing the same thing kind of here for speaking instead of other things. But here is where they talk about how the ear works, where you have your ear canal, your eardrum, all this stuff is filled with the fluid inside of your ear, and these are the bones inside of your ear. I still don't give them their proper names, but that's okay. Oh, here they kind of do. The hammer, the anvil, the stirrup, the pivots, the window, and so on and so forth. And here they have them in more detail here. You have this bone that's near your eardrum right here, and you have your hammer and your anvil, the stirrup, and all these things they feel the eardrum moving. They move when the eardrum moves, and they transfer all of this stuff to your oral nerve, which is here, and here is all this other stuff that sends it that way, sends this pressure wave that way. And again, we're not going to be, using that in this course in any kind of calculation. It's just understanding it. Ultrasound is sound that is above the frequency of hearing that we have, so above 20,000 hertz. And here they're using ultrasound pressure waves to look at a fetus inside of a mother's womb. So here you can see the nose, the hand. You can see that they're sucking their thumb. There's their head. The lighter parts here are hard bone usually. So when you're seeing the skull from the side, you're seeing a lot of bone from the side along the edges. And you can see that the baby has soft spots on top of their head, where there's not much bone, and that's normal. And then you also usually see the spine, which looks like it's right about here. You can see the femur, or actually the shin, which is the whatever that is. But anyway, you can see that bone there. You can see some facial bone here. And that is because the sound waves bounce off of bones differently than they bounce off of fluids. And so the fluidic parts are darker and don't get as much bounce, and the bones you get more bounce, and you see it brighter. See it as a brighter light there. You can also use ultrasound therapy to break apart tumors. And so here's a tumor inside of the brain, and they send in this little ultrasound, kind of like a hammer, and it breaks apart the tumor so that the tumor won't grow anymore. And they use ultrasound for lots of things, really. Here they want you to calculate acoustic impedance and intensity reflection coefficient, which they actually give you the equation for. The intensity reflection coefficient A is calculated here using the numbers that they're essentially just going to give you, which are acoustic impedances. So you're good to go here. They tell you how to calculate the impedance using the density, and this and the V, I guess, is the speed of sound in the table here. Yeah, speed of the ultrasound in this table here. So anyway, it's just stuff they give you the information you need to know to calculate those things, and it's interesting stuff for sure. If you want to become an ultrasound technician at all, you have to usually use your physics quite a bit. So you need to take physics to get to that level, and it's a fairly interesting job and well-paying job. They have 3D ultrasounds, which are getting more popular. Calculating the velocity of blood using Doppler shifted ultrasound, and that's kind of interesting. So here they're actually going to be sending ultrasound into the blood, and the blood bounces off of the moving blood, the sound bounces off of the moving blood cells, and as it comes back we can measure the Doppler shift. In other words, how much the sound changes as it bounces off of something that's moving. And so we're going to be using the Doppler equations, frequency observed here. Where the sound of the source of the sound is stationary and the object that is encountering the source is not. And that's about it. That's chapter 17 for us, and we're finishing up this semester, and it's good because the street sweeper is coming. If you have any questions, I will be available.